In this session, we study combination of thin lenses in contact. Now, you all know if the paraxial rays are incident on a lens, either they will converge to a principal focus or they appear to diverge from a point. Now, that distance is nothing but the focal length. If the paraxial rays are incident on a system of lenses instead of getting incident on a single lens, if the paraxial rays are incident on a system of lenses which are combined coaxially, which are arranged coaxially. What do you mean by coaxially? It means their optic centers lie in the same line or same axis. Then that arrangement is called as, or the lenses are said to be placed coaxially. Now, if the paraxial rays are incident on such a system of lenses, then what will be the focal length of that whole system? What will be the effective focal length of the system or of the combination of lenses? To understand that, consider a system of two lenses A and B of focal length f1 and f2 placed in contact with each other. Let the object be placed at point O beyond the focus of the first lens. Why we have to place beyond the focus? Because if you place the object beyond within the focal point, within the focal length, then the image is going to be virtual and on the same side of the lens. To have a real image by the first lens, the object has to be placed beyond the focal point. So let O be the object which is placed beyond the focus of the first lens. Now, the first lens produces an image I1. So, here we are considering the final image formation in two steps. First, you have to assume that only one lens is there. The second lens is not there. So, when the incident ray from the object O is incident on the first lens, it gets refracted and produces the image at I1. Since I1 is real, because we have kept the object beyond the principal focus and it is the convex lens, it produces an real image. So since image I1 is real, it serves as the virtual object for the second lens B, and then the second lens produces the final image at I. Now, since these lenses are thin, we have to assume their optic centers are coinciding. Let that point be P. Now we'll write the equation for refraction at two lenses. First we'll write the thin lens formula for the image formed by the first lens. The formula is 1 by V minus 1 by U is equal to 1 upon F. The image distance, reciprocal of image distance minus reciprocal of the object distance is equal to the reciprocal of the focal length of that lens. So for the first lens, V1 is the V1. I1 is formed at a distance of V1 from the first lens. So V1 is the image distance minus U is the object distance is equal to 1 upon F1. Let this be equation 1. Now we'll apply the same thin lens formula for refraction at second lens, image formed by the second lens. Again 1 upon image distance. Now which is the image? Now this ray, refracted by the first lens, that ray acts as the incident ray for the second lens, and then it produces the final image at I. So this ray which has been refracted by the first lens is responsible for the point I dash. So for this incident ray, I dash serves as the object. So 1 upon image distance is 1 upon V, because the final image formed by the second lens is at a distance of V. 1 upon object distance, the image formed by first lens at V1 serves as the object for the second one. So it will be minus 1 upon V1 is equal to 1 upon F2. When you combine both the equations, you are going to get 1 by V minus 1 upon U is equal to 1 upon F1 plus F2. Let this be equation 3. Now if the combination of two lenses, here is the object placed, by getting refracted through both the lenses, after getting refracted through both the lenses, here is the final image that is going to be produced if this is the U value, V value for the system of two lenses. If the system of two lenses is replaced by only a single lens which is having a focal length f, for which you are going to place the object at U and it is going to produce the image at V. So for that lens which is having the focal length for the object distance U and image distance V, we can write the thin lens formula as 1 upon V minus 1 upon U is equal to 1 upon F. Now compare this equation 3 and 4. Their LHS are same, so we can equate the RHS of both the equations. That is 1 upon F is equal to 1 upon F1 plus 1 upon F2. So here we have derived it for system of two lenses, combination of two thin lenses. But this derivation is valid for any number of thin lenses in contact. If several number of thin lenses of focal length f1, f2, f3, f1, f2, f3, f4 are in contact with each other, then the effective focal length of their combination is given by 1 upon f is equal to 1 upon f1 plus 1 upon f2 plus 1 upon f3 and so on. Now the same equation we can write in terms of power, because power is equal to 1 upon f. So 1 upon f can be replaced by P. The power of the combination of the lenses is the sum of the power of individual lenses, individual powers of the lenses. So you can note that effective power is an algebraic sum of individual powers, because if one lens is having plus 2.5, another lens that you are combining is a concave lens which is having minus 0.5 power, then the net power, effective power of the combination is plus 2.5 minus 0.5. It will be plus 2 dioptra, or F is equal to 1 upon P, 1 upon 2. 1 upon 2 means 0.5 meter or 50 centimeter. If you combine the two lenses, one is convex lens, another one is concave lens, both are having the power. One is having 0.25 plus and another is having minus 0.5. When you combine them, then the effective power of that combination of two lenses will be 2 dioptra. It means the combination of that two lenses acts as a converging lens, because at the end you are going to get a minus plus sign. Plus means the combination lens is equivalent lens will be convex. convex lens of a focal length 50 centimeter. So sum of the terms on the right side of the equation may be positive. P1, P2, P3, P4, among these, some of the terms may be positive or they may be negative depending upon the lenses that you are combining in a system. If you combine all the lenses, convex lenses, then the powers on right hand side of this equation will be positive. Now, since the image formed by first lens becomes the object for the second lens, the total magnification M of the combination is the product of the magnification of the individual lenses. You may ask why the power is getting added, and here in terms of magnification, the total magnification is the product of the magnifications. It is because the image produced by the first lens acts as object for the next lens. For example, if you take a lens with a magnification 3 and we are placing an object of 1 centimeter in front of it. Magnification 3 means, what is magnification? M is equal to h dash by h. If m is equal to 3 means h dash by h value will be equal to 3 or 3 by 1. Means the ratio of the image size to the object size is 3:1, or your image is 3 times the size of the object. So the lens is giving the magnified image 3 times that of the object. So after refraction, the lens is going to produce a magnified image 3 times that of the object, so it will be 3 centimeter. If you place a lens of 4 magnification is equal to 4, then whatever object is there, its size will be 4 times that of the image produced by this object will be 4 times that of the image So if it is a 3 centimeter, m is equal to 4 means it is h dash by h. H dash is equal to 4h. H dash is equal to 4 into h is 3 centimeter. So h dash is equal to 12 centimeter. So initially, before the combination of the lenses, in front of the combination of the lenses, the object placed is 1 centimeter. At the end of the combination of the lenses, the image you are getting is 12 centimeter. The magnification of both the lenses are 3 and 4. So the effective magnification that you are getting is 12, the multiplication of both. So the total magnification of the combination is the product of the magnifications of the individual lenses. Such a system of combination of lenses is commonly used in designing lenses for cameras. Lenses for cameras, or sometimes to have a magnified large images. If it is not possible to have a desired magnification by a single lens, then we can have the combination of two lenses to get the desired magnification in the object image size, and such a system is also used in microscopes telescopes and other optical instruments.